If our algebra contains only non-abelian ideals, but it doesn't contain abelian ideals,
that's right.
Can we still call it semi-simple?
Yeah. Right. So, I mean, the simple algebra is the one which has no ideal at all, right? No proper ideal. But semi-simple would be basically direct sums of simple algebras, no? So, in general. Because, yeah, I mean, whatever the ideal semi-simple has must be not abelian. Yeah, that is the point. So take any direct sums. I mean, for example, SU2 plus SU3, whatever. No? Direct sums of such algebras. These are all simple algebras. Now, if you take, for example, already this one here. So this algebra basically contains it's a pair of elements. I mean, so you have basically the x's and say let's call it y's, the Lie algebra elements here. So xi with yj is 0, right? That's what direct sum means. The Lie algebra of this SU2 and the Lie algebra of that SU2 commutes. Okay. So is that clear? I mean, the total dimension of the direct sum is a sum of the two dimensions, right? So this is 3 dimension. So this is 3 plus SU3 is 8, right? That's 11 dimensional Lie algebra.
Could you generalize this proposition? So we say that for any Lie algebra we can write as sum of semi-simple Lie algebras plus an ideal.
Repeat it again, I cannot hear.
I want to generalize this formula. So not only for simple Lie algebra, semi-simple Lie algebras. So for any Lie algebra, we can write a sum of semi-simple Lie algebras plus an ideal. Could we do that? Yeah,
but I mean, it will not be direct sum in general, no? Like we saw for the Poincare group, right? Poincare group is not. So there's a translation subgroup there, and of course the Lorentz transformations, but they do not commute with each other. So it will not be direct sum in one case. But it's called, I mean, so in general there would be a semi-direct. So direct sums, the direct sums are this type, what I just wrote down. Right? The direct sums are of this type where the Lie algebra of element of this and the Lie algebra element of that commutes, right? Exactly. But for that, I don't know what is the notation for that, but Poincare algebra is the Lorentz algebra, and the direct, not a direct sum, but let's put here S just to indicate it, semi-direct. I don't know what is in the standard, probably different books have different notations. So this is semi-direct sum. So that is plus the translation. Okay. So unlike here, now here what happens, so let me call it L. L is a generator of Lorentz algebra and T is a generator of translation, right? Then L with L is again L, is again in the Lorentz. T with T is of course 0 because they commute, right? But L with T is again T, right? Translation. So these do not commute to each other. So there's a semi-direct sum. This is called semi-direct sum. So this will not be, I mean, whatever it is, semi-direct, even though it's semi-direct sum, still the translational algebra is a sub-algebra, right? Because it's clear, I mean, T with T is part of T, it actually is 0, but so therefore it's a sub-algebra, right? And it's also an ideal because you see T with L is again T, right? So T is an ideal, the translation is an ideal of this algebra, but it's also abelian, right? So therefore this is not semi-simple.
And what if there were anti-commutation relations apart from the commutation relations? Would the symmetry corresponding to that generator be also a semi-direct sum, or would be something different?
It will be something different. I mean, yeah, in this whole discussion, we are really talking about bosonic algebras.
Yes, but
Yeah.
how is it called if you have that case? Instead of a semi-direct sum, what would be?
And it depends on the algebra, what kind of algebra you're talking about. Supersymmetry algebra would be rather complicated. I mean, supersymmetry algebra would be, you have, plus there will be also the fermionic supersymmetry, SUSYs. SUSY with SUSY will give you translation.
Yeah.
Will give you a translation. Okay. Now, I mean, SUSY with SUSY, of course, you have to take the anti-commutation relation here. Okay. So it's a bit more different situation. Yeah. No, so whatever I'm discussing is really bosonic algebras, no, not supersymmetry.
I don't want to go to something else in this question. It's okay.
Okay. I mean, I don't know if there will be extra lectures on, towards the end of this year, if there will be extra lectures on SUSY. But as I told you, we used to have it. Some very brief course, one week course or something.
Does it make a lot of difference if we use anti-commutative instead of commutative in DL?
Yeah, it's a different thing. I mean, it's a totally different. Yeah, totally different.
So it means that all the theorems that we are learning for the algebras are only for if it is commutative.
Yeah, I mean, we are just focusing on the bosonic algebras, right? Yeah. Okay, so now let's. But is there any question on the last? Because last time we started discussion of the general structure, not just some specific examples, SU2, SU3, etc., but a general discussion about the semi-simple algebras. So the aim of this last time's and today's lecture is mainly to show to you how powerful is this. Once you have semi-simple algebra, that is the Cartan killing form is non-degenerate. Basically, you get the kinds of algebras that we have already seen, the SU2, SU3. No? The basic features of the algebras are the same. Just like in SU3, you have various SU2 subalgebras, right? The same kind of feature will appear in general, just from the semi-simple. Right? So this is the main aim of it. Let me see, which chapter was it? Chapter 12, right? Yeah, correct. And we had done the theorem 12.3. Is there any question on theorem 12.3? Last time we did 12.3, and so if there are no questions, I'll move on to 12.4. Okay? Any questions on 12.3? No, so that's just fine. So just to state the main point was that the full Lie algebra G was the direct sums of the Cartan subalgebra, and the sums, not direct sums, sum of the Cartan as a vector space. It is the Cartan subalgebra, and then there are non-zero roots. So alpha belong to delta. Delta is a set of roots. Delta is a set of roots, set of non-zero roots. Okay, and for each such alpha belonging to delta, there will be some vector space which I call G alpha, which may or may not be one-dimensional. In SU2 and SU3, we found that this is always one-dimensional, right? But we have to see it in general whether it's true or not. Right? At the moment, we don't know whether it's one-dimensional or not. So this is the basic as far as the vector space is concerned. Vector space. That was the first statement. The second statement was that if so alpha beta belong to delta, then the commutator of G alpha with G beta will be in G alpha plus beta. Right? This was again, we have seen it again many times, because when you take the commutator of the any elements, let's say X alpha, take some element here X alpha, some element here X beta, and if I take the commutator, whatever the result is, it will have eigenvalue alpha plus beta, right? That is just, the statement is just that. So it could be 0, but if it is not 0, it is going to be inside G alpha plus beta. Well, 0 is of course also an element of that, right? Every vector space is 0. So this is always true. And that just follows from the fact that if I take the commutator of this x alpha x beta, that you find some h, then this will be alpha h plus alpha plus beta h times x alpha. And this just again comes from the use of the Jacobi identity. No? So you write it as a h commutator with the x alpha, one term, another one h commutator with x beta, and that gives you that equation. Third, so again alpha beta group, if alpha plus beta is not equal to 0, then b x alpha x beta is 0.
Can you close the door because the voice recordings is not clear? So can I close the door?
Sorry, repeat that again?
We need to close the door.
Yeah. Okay. This was again, you could just see that, I mean the basic way to prove it is just use the definition. I mean again, I just quickly repeat. So we are looking at add, say x alpha, add x beta, and we want to take the trace of that, right? That is the b, right? So before taking the trace, let us see what happens if I apply this on x gamma. Okay. Well, when I apply this, this is of course a commutator of x beta, x gamma. So this part, if I just look at this part will be some element of x beta plus gamma, right? If it just follows from the previous one. Now if I apply add x alpha on that, which means a commutator of x alpha with x beta plus gamma. So this is going to give me something which is of the form alpha plus beta plus gamma. Right? It will have the eigenvalue alpha plus beta plus gamma. That is the action of these two guys. Okay. So what it is saying that this operator takes x gamma to x alpha plus beta plus gamma. But finally we want to take the trace to compute the b, right? But so if alpha plus beta is not 0, then you see x gamma is going to something different. X gamma plus this non-zero term. So that this operator is completely off diagonal, right? So therefore the trace will be 0 because trace is the diagonal element. So that is so this is an important statement actually. I mean it's very trivial to prove, but it is very powerful, as we will see. Then for Cartan-Killing form B restricted to the the Cartan subalgebra is non-degenerate. Okay. Then the fifth was if alpha belongs to delta, then minus alpha also belongs to delta. Okay. This is again coming from this. Both of these statements, this and that, is coming from this here. Because if I take h here, so which means alpha is equal to 0, right? Then the only way this can be, whenever beta is not equal to 0, then of course that will be 0. So in other words, if I choose alpha is 0 here, right? Then that means it's part of the Cartan subalgebra, 0 root Cartan subalgebra. Then whenever beta is not equal to 0, this is 0, right? So the only time when it may not be 0 is when this is also 0, which means this is also Cartan. So the only way, if you have a Cartan here, the only way B might not be 0 is if the second element is also Cartan, right? So the whole thing becomes completely, if I write the B in this basis, H, so let me write it like this, H and various x alphas and so on, x beta, etc. Then if you look at the B, in this, so it will be purely block diagonal. So this part will always be 0, and here there will be something, here there will be something. Right? This is the structure, right? Because of this fact. If this is in the karta, then that also has to be karta. Otherwise, it is 0. So the B will be of this form in this basis. Once I choose this basis. So then the determinant of B will be determinant of this times determinant of that, right? So, and since I know that we are talking about semi-simple, the determinant of B is not 0, that implies the determinant of this is not 0 and determinant of that is not 0, both. No? So in particular, determinant of that is not 0, that is the statement. And similarly, this statement is also coming from that, because if I look at x alpha, the only way this will be non-zero is if beta is minus alpha, right? Everywhere else it will be 0. So the structure will be, if I put here x alpha, if there was no x minus alpha, then this entire thing will be 0, this row will be 0, right? And the determinant will be 0. So the only way it can be, it is not 0, is if x minus alpha is here, also exists, and then of course this block, if I look at this block, this two-dimensional block, then it will be of something of this form, right? And then of course what it would say that this determinant is not 0, right? If these are not zeros. So this is the statement here. And finally, we also proved number 6 was that the alpha belonging to delta spans its star H, the dual space with that. I mean, sometimes, sorry, this is really, this is the set, this is a vector space. Many times I use the same symbol for the element, no? But I mean, how, I don't know, you have to probably write something like that. Huh? You have to probably write something like that. So this is the vector space, the Karta subspace. Okay. So this is also H star. Okay. So now we go to the next. So we want to now go to theorem 12.4. That is where we stopped yesterday. On Friday. Okay. So Thursday, that is. Yeah. So the first statement was that which we already used, that given the non-degeneracy of B, say suppose alpha belongs to delta, then I look at all this alpha H. So alpha H was just the eigenvalue so this was simply that H x alpha is alpha H x alpha. What is the eigenvalue of H? For any H, right? For all H, this will be, so this is just some number. So alpha, that is why alpha was in the dual space. Alpha is a kind of linear function on the Karta subalgebra. So given the alpha H, you can define, using the fact that the Cartan-Killing form is not degenerate, you can define a unique element H alpha define a unique element H alpha belonging to the Cartan subalgebra, okay, such that this statement is true. Okay. We have already used it before. We had constructed for SU2 and SU3 case. We discussed that, right? Now there we have put a C also here, CG, but we are here. I mean, this discussion is unimportant. I mean, it's irrelevant whether you put a CG or not, or put CG equal to 1. It doesn't matter. So just so that we don't keep that CG hanging around throughout, I just put that equal to 1 there. Because it's a matter of, if I put a CG here, you can absorb that CG inside here, H alpha, and then just redefine your new H alpha. No? Because this is bilinear. You can put any number inside. No? So that's not important. So CG becomes useful when you discuss specific algebras. No? So by choosing appropriately CG, you can simplify some numbers. No? Instead of getting fractional numbers, you get integers and so on. But other than that, it's not important. Okay, so then it's unique. You see, here this is where we are using very crucially that the B is non-degenerate. Okay. Because B is non-degenerate, we can, given an element in the H star, which is alpha, alpha is one of the elements of H star, I can find uniquely an H alpha. That's this is like raising and lowering of the indices, no? So if I have alpha I can use the Bij to raise it. Raise it to alpha I, which is equal to Bij alpha j. This is the kind of thing. This is raising and lowering. But this can only be done, both ways. Only if B is non-degenerate. So that's the. So that's a definition of H alpha, and we know that this is guaranteed to exist. Okay. So now the theorem 12.4 is saying. So the first statement is that X alpha with X minus alpha. So let's say alpha belongs to a root. Then of course there must be some X alpha, and from the previous theorem we know therefore there must be some X minus alpha. No, that because of a non-degeneracy. This statement. So I choose that. Now I take the commutator of these two. Now what is it going to be? It's going to be in the Cartan subalgebra, right? Because whatever appears here will have the eigenvalue this plus that. But alpha minus alpha is 0, so it must be in the Cartan, right? But the question now, one can ask the question, which Cartan element? I mean, we have the full H. This H is a some-dimensional space, vector space, right? But which particular H appears here? Okay. This is important because you remember, like in SU3 case, when we had alpha 1, the roots alpha 1, alpha 2, and so on and so forth, we had X alpha 1 with X minus alpha 1, and that, remember, came out to be H1 up to some number, H1, right? So this is what, this is what defines to you one SU2 subalgebra, right? So what appears here, specifically which H appears there, is important because that is what's going to give me the one SU2 subalgebra. No? Okay. And the statement is that what appears here is actually that H alpha. Not something else, but that H alpha, which is defined from this equation. Okay. Up to some number. And that number is in fact Bx alpha, X minus alpha, H alpha. This is a statement of 1. Huh? So let's go through this proof. Okay, so the statement again basically just uses Jacobi identity. So let's see. So we want to take B of this X alpha, X minus alpha, with say H. H is arbitrary. This H is arbitrary. So H belongs to Cartan subalgebra. Okay. So the logic is the following: if you are making such a statement, then that means if I take the Cartan killing form between this and an arbitrary Cartan element H, right? Then that better be equal to the Cartan killing form between this and that the same arbitrary element H, right? That is what we want to check. And if you are able to prove that, then that is it. Because Cartan killing form is again non-degenerate, and since this is true for all H, then this must be true. You see, that is the logic. So let's start from here. Well, what is this? This is nothing else but the trace of add X alpha, add X minus alpha, commutated with add H, right? Add H. So we want to take the trace of that. But now you can rewrite that using cyclicity property. This is two elements. This times that minus the other way around, right? And the second term, you can bring add X minus alpha on the other side by cyclicity, and this is the same as trace add x alpha and the commutator of add x minus alpha, add x minus alpha with add h. I think this you have done also in one of the problems probably. So in other words, it's the same as b x alpha x minus alpha h. But this commutator, this is the same as minus, so this is the same as minus b of x alpha h x minus alpha, right? I mean, if you change the order, commutator picks up a minus sign, and minus 1 is just a number, so I can take it out, right? Because this is bilinear, b is bilinear in the two arguments. And then this is nothing else. This is nothing else but minus alpha h acting on x minus alpha, because this is eigen states. So you get here, so minus minus cancels, make it plus. So alpha h, and alpha h is a number, so I can take it out. B of x alpha, x minus alpha. Right? But then I use that definition for the bh alpha. So we find this is the same as b h alpha h b x alpha x minus alpha. Okay. Then again, I mean, this is a number, right? So I can rewrite this expression as b of b x alpha x minus alpha times h alpha comma h. Right? This is a number, so I can multiply that number to h alpha, so you get that. Now compare these two sides. See, this is true for arbitrary h, right? And since b is not degenerate, I mean, or another way to do is to write like this b of, so just put them together. So we said this is equal to that. This is equal to that. So take it on the other side. So that's the x alpha, x minus alpha, minus b x alpha, x minus alpha times h alpha. This is one element, I mean, this is a particular combination with any h is equal to 0 for all h belonging to h. And since we already seen that, I mean, this is certainly an element of the karma, right? And since b is not degenerate in the restricted to the Kartha subalgebra, this implies that this itself must be equal to 0. And that proves the statement here. Okay. This is very, I mean, it's very important, because this is really telling you which SU2 subalgebra. I mean, that SU2 subalgebra involves which Kartha, a particular combination. This is a very fixed combination. Okay. Is there any? I mean, just to stop. So we think about it. See if there's any questions, doubts on that, on this proof.
You put alpha h instead of minus.
And there are two minuses, right? I mean, so here I can rewrite this as minus. I mean, that is I just change the order. So h x minus alpha. But that h x minus alpha is minus alpha h. What is that? No. So I already put the minus. Sorry. Before it was this, right? I already changed the order to make it minus. Okay. And this itself is minus alpha h times x minus alpha. I mean this part. If it was plus alpha, this would be plus alpha h, right? The x minus alpha is precisely defined like that, no? That it has exactly the opposite negative root compared to that, negative eigenvalue with respect to that. So it's, and then this minus minus cancels. Okay. And finally, there's a second part of this theorem, theorem number 1, which is that, I mean, this was what? This was one particular, I erase that, because we decompose the full G, the algebra, in terms of the H plus G alphas. So these are the subspaces which are root alpha, which are eigenvalue alpha. We don't know yet it's one-dimensional. We'll prove that it's one-dimensional. For the moment, we don't know it's one-dimensional. Could be at this stage any dimensionality, alpha belonging to delta. Right? So what we did here, we picked up one element of G alpha, one of them, say X alpha, and since I know from the previous theorems that there must also, for given alpha, there must also exist, if alpha is a non-zero root, there must also exist G minus alpha. So from G minus alpha, I picked up another X minus alpha. And this is what we get. Okay. But you see, the H alpha itself is defined completely given the alpha. Once you specify alpha, this H alpha is defined uniquely, right? So it doesn't matter which X alpha you have picked from here, right? Suppose there is another one, Y alpha in G alpha, which is independent from X alpha. Okay? That's also going to give me the same H alpha, because this didn't refer to which element you're talking about. This is simply that quick issue. That given the alpha H, no? So this is fixed completely. This is fixed by specifying alpha, not which element of G alpha you're taking. You see? So therefore, even if I write full G alpha and G minus alpha, okay? So arbitrary element of G alpha I pick here, an arbitrary element of G minus alpha I pick here. Whatever it is going to be proportional to H alpha with some number. That this number may change. If I choose a different, instead of X alpha, I choose some Y alpha, this number may change. But H alpha is going to be the same, right? That is why it is some complex number in general, because we have complexified everything, right? So this could be some complex number times H alpha. So that is the statement of that. Now the second part of this theorem in the 12.41. Yeah? This is the first statement. So all of them give the same H alpha, right? This would be, I mean, this is a bit, so remember we want to prove that there is always an SU2, right? Now, if there was an X alpha, X minus alpha, and also there is another Y alpha which is linearly independent of X alpha and Y minus alpha, this also gives you some number times H alpha. This would not be a very nice situation, right? Because the same H alpha is appearing in two different SU2s. Okay? So in fact, so we'll prove that actually dimension is 1. Okay, dimension of this space is 1. Now, the second part of the theorem is, you see, there's one more thing we need to show, right? Okay, we want to interpret this as an element of SU2. I mean, let's say take this SU2. Some SU2 subalgebra defined by X alpha, X minus alpha, and H alpha, right? So now in SU2 subalgebra, a standard SU2 subalgebra would have H alpha. H alpha should give you in other words, if I compute the B of H alpha, this would be not zero, right? I mean, SU2 sigma 3, sigma 3 is in the H, right? If you compute the B of sigma 3 with sigma 3, this is not zero, right? I mean, you just take the adjoint of sigma 3 and take the product and the trace. That will not be zero. That will be, I think, 2 or something like that, right? So we want to check this question. We want to ask the question, could it be zero? And the answer turns out to be this. This is not zero. So that's the second part. And the third part is also an interesting part, that dimension of G alpha is equal to 1. And furthermore, this is again another very useful thing, that dim of G and alpha is equal to is equal to Z, equal to 0 except for n equal to 0 or plus minus 1. So n equal to 0 is fine, because n equal to 0, this is nothing else but the Cartan subalgebra, right? Because n is 0, so this is 0 root, right? But what it is saying is that, for example, so plus minus 1 is also fine. Plus 1 is just the original G alpha. Minus n equal to minus 1 is x minus alpha, G minus alpha. Okay? But what it is saying is that, for example, if I take n equal to 2, this is 0. Okay? So that means if x alpha is a root, if alpha is a root, then 2 alpha is not a root. I mean, this you saw that. I mean, in SU3 you had this alpha 1 and then alpha 2, etc. But you didn't have a 2 alpha 1, right? Because that would be a bit strange. Because 2 alpha 1, suppose there was a 2 alpha 1, then you will have again another SU2 subalgebra, 2 alpha 1 minus 2 alpha 1, no? And alpha 1 minus alpha 1. Both will have H1 as a Cartan part. This would be weird, right? So that is the importance of this theorem again, right? That you really have SU2 structure, not some exotic thing. Huh? Okay. So how does one prove that? The method of proof itself is would be very interesting because this kind of method will be used again and again. So please focus on the method or even to prove this. So the idea is the following. I mean, so we have this big adjoint. So we have this adjoint representation. Is of course has a dimension. So dimension of the adjoint representation is the same as dimension of the Lie algebra, dimension of G, right? Is a big thing. But what we will do is we'll start taking some subspaces of this. The idea is to take some subspaces which are kind of geared for this SU2 subalgebra. Okay. So we will be basically using this SU2 subalgebra, x alpha, x minus alpha is equal to some h alpha, some number times h alpha, right? So we'll be using these three generators, x alpha, x minus alpha, and h alpha, okay? And start constructing some subspaces inside this big space, some subspaces, such that this algebra closes. I mean, this algebra does not give you anything out of, if any of these generators, x alpha, x minus alpha, and h alpha, so what we want is that we want to look at some subspaces. Let's call it V, which is inside I don't know, let's say dimension of G is say say n, okay? Then this adjoint representations can be thought of as something acting on an mth column vector, right? Because all the generators can be written as m by m matrices because they're going to just transform the different. So so V is in some subspace of Vm. Vm is the full space, let's say. Okay, Vm is the full space, and we want to construct some subspace such that these three generators, x alpha, x minus alpha, and h, take V to V, and not something outside. Huh? Why we are doing that? Because you see, then you can start using you can start computing the trace of h alpha. No? So idea, okay, maybe it will become clear. I think once I go through this, the first proof. So we'll construct this space in the following way. Okay. Well, so we are saying alpha is some root. Okay, alpha is a root. Alpha belongs to delta. So first step here is that, so of course for alpha belongs to delta, so that we already know H alpha from that definition. H alpha is defined. H alpha is defined from here, sorry. H alpha is defined here, right? H alpha is defined from that equation. Okay. Then we are saying that since we know that so there must exist some beta belonging to delta, okay, such that B of H alpha H beta is not equal to 0. Okay. You see, our aim is to prove this, but what we are saying is that okay, we don't know whether this is 0 or not 0, but since I know the B restricted to the Cartan subalgebra is non-degenerate, there must exist some H beta, right, such that this is not 0. Okay. So there must exist some H beta, and here we have used both the non-degeneracy of beta of B and also the fact that alpha spans roots span the entire dual space. No, that was the previous one of the previous theorem. We said the non-zero roots span the entire dual vector space. So there must exist some beta, H beta, okay, such that this is not 0. Okay, so pick one of those betas which satisfy this condition. There may be many more than one betas which satisfy this condition. Pick one of them, okay. And then consider this chain. So we construct this V, this space, subspace V, which is G beta plus n alpha, summed n belonging to all integers. Okay. I mean, of course, this sum is a finite sum, even though I'm writing it as infinite sum, because this will be, I mean, only those n's will appear for which beta plus n alpha is a root. No, otherwise this is not this empty. No. So even though I've written it as like an infinite sum, but actually it's a finite sum, because we are always assuming that's a finite dimensional Lie algebra. So this dimension, the full dimension, this m is finite. So this cannot go up to infinity. It's just saying that wherever, for whichever n, beta plus n alpha exists, I'm summing that up. That's the statement. Okay, so we take this. Now, so let's see. So our claim is now that this V, when x alpha, x minus alpha, I mean add of x alpha, add x minus alpha, and add h acts on this space, then you get back again the same space. Okay? Not something outside the space. Because the full space is bigger. Full space is not just that. I mean, there are other roots which are not of the type beta plus n alpha. No? Some other root gamma which is not of the type beta plus n alpha. In SU3 case, it was not so, because it was only two-dimensional. I mean, Cartan subspace is only two-dimensional, right? But not in general. In general, high-dimensional Cartan subspace subalgebras, it won't be in general true. So it will be some subspace. Okay. Now let's see. Let's first check that this vector space is closed under this action. Okay. Well, when add h acts on this, then of course each of this G beta plus n alpha goes to G beta plus n alpha, right? Because each of them is an eigenstate of H. So you're just going to get, I mean, if I take some x beta plus n alpha, it is just going to be equal to beta plus n alpha H acting on times H times x beta plus n alpha, right? Because these are the eigenstates. So this is some number times, right? So add h takes G beta plus n alpha to add h takes to G beta plus n alpha. This is fine. Okay. So therefore add h leaves takes an element of V and brings it back to V, because add h takes each of them and brings it back, right? So therefore, of course, a sum also. So this is a sum here. Then let's look at add x alpha. What it's going to do? Add x alpha acting on this. Well, we know that what happens. The eigenvalues add up, right? So it's going to give me beta plus n alpha plus alpha, right? So this is going to be inside G beta plus n plus 1 alpha, right? And since I'm summing over all possible n's, this space is closed under the action of x alpha, right? And same thing with the x minus alpha. If you add x minus alpha on this g beta plus n alpha, you're just going to get g beta plus n minus 1 alpha, which is again part of the sum, included in the sum, right? So therefore we see that this space is closed under the action of x minus alpha, x alpha, and h alpha. I mean, it's closed under any h, so in particular also h alpha. Any Cartesian element is closed, but in particular h alpha also, right? Okay. So then suppose now I take the trace of add h alpha, okay, in this subspace V, not the big space but V, okay. So I take the trace inside it. But this add h alpha I can write as trace because this satisfies the commutation relation, right? So this is the same as add x alpha and x minus alpha commuted, right? Up to some number. I mean, this commutation relation gives me b, so let me write it as b x alpha x minus alpha times that. Because this commutator just gives me that bx alpha x minus alpha and h alpha, right? This was from the previous part of the theorem. We proved that the commutator of these two, it just gives me bx alpha bx minus alpha times h alpha. Okay. So I use that, and we can pick, of course, those alpha and minus alpha such that this is not zero. We are guaranteed that such an x minus alpha exists, that this is not zero. Okay. I mean, this is from non-degeneracy. So I do that. Inside again the V. We again take the trace inside V, which is okay because each of them. So you see now we are thinking of each of these guys as if suppose V has a dimension, the full dimension was m. Let's suppose V has a dimension k, right? Which is in general less than or equal to m, right? Then we are thinking of these guys now as a k by k matrices. Okay, and this is perfectly okay because this one, each one of these terms acting on this k-dimensional space takes you back to k-dimensional space. So you can think of them as k by k matrices. Okay, so this trace is over this k-dimensional space, not the full m-dimensional space. Okay, but now you can use the cyclicity property. So this is zero because trace of any commutator is zero, right? The cyclic property. So use cyclicity. Cyclicity. So it's zero. Okay, that's fine. But we can also calculate directly what this is, right? Because we know for in each of the subspaces, this will just these are all eigenfunctions of this h alpha, right? So I can compute directly the left-hand side. So compute the left-hand side. So we directly compute the left-hand side. Left-hand side of that equation. So in other words, we compute trace of add h alpha in the space V, but the space V was the sum of these spaces. So this is the same as sum n belonging to integers and add h alpha acting on g beta plus n alpha, right? But in each of the subspaces, add h alpha is just a diagonal proportional to identity matrix, right? With a diagonal entry being, so what is it? Look at this, how add h alpha acts. H alpha acting on g beta plus n alpha. This is nothing else but beta plus n alpha acting on h alpha. I mean, this is the eigenvalue times the identity matrix 1 1 1 what identity matrix, where this is matrix is the dimension of the this matrix is dimension of this space of g beta plus n alpha. Right? I mean, suppose this has some two-dimensional, let's say. Suppose this space is two-dimensional, right? So there are two linearly independent vectors here. But each of these vectors give you that. I mean, this is going to be the each of them will be eigenfunction with respect to this Cartan subalgebra, right? So eigenvalue is this, right? And it is the same for both of them. That's why it's identity matrix here, right? Here I've drawn it as 4. So think of this as a 4-dimensional, for example. Then it will be a 4x4 identity matrix times a number, and that number will be the eigenvalue. Okay. So therefore, this trace becomes sum n belonging to the integers, and you get here beta. So what is beta acting on H alpha? It is beta acting on H alpha is the same as, use that definition, beta acting on H alpha is the same as H beta H alpha. Right? So it will be, the first term is beta B of H beta H alpha, this term, and then you have n B H alpha times, let's say I call it D. D is a dimension of this space, beta plus n alpha. So this is the dimension. This dimension I'm calling. So D beta plus n alpha is equal to the dimension of this space. This vector space. Huh? And I have to sum over all this. That is the trace. So what I did, first of all, on general argument, we proved that this is 0. And that is why, because I can write this as a commutator. Right? But it is important that for this we need to have a space which is closed under the action of all these 3 generators. You see. I mean, you couldn't have, for example, if I had, suppose it was not closed. Suppose add x minus, so let's say there are 2 terms here. Add x alpha. So let's look at the first term, which is this, in this order. Add x minus alpha, acting on V. Okay, V is some k dimensional, right? But suppose that this space was not closed under the action of this, right? Then you cannot write this as a k by k matrix, right? So let's say when it acts on this, it takes you out of this, outside this, okay? Then it would be a rectangular matrix, not a square matrix. It could be some k plus say something, k plus s, let's say, comma k matrix. Okay. In that case, it wouldn't make sense. You see, you cannot. So then you cannot use the cyclicity property. Cyclicity property is only meaningful when you have square matrices, right? Otherwise, you can't move it around. So that was why it was crucial to construct this a subspace. Of course, you could have taken the full space also, but that doesn't give you much information. Huh? We want to pick up some subspace which gives us some useful information. No? So we picked up this particular subspace, and since it is closed, this space is closed under action of each one of them, right? Then I can use the cyclicity property of the trace. Okay. And then so that vanished. We already know it vanishes. But on the other hand, I directly can calculate it, and that is this calculation. So this better be 0. That's a calculation, right? This better be 0. On the other hand, by assumption that we are saying that we have picked up the beta such that B of H beta H alpha is not 0. So this, I mean, that is how we picked up. We picked a particular beta such that this is not 0. So this is not 0. And the whole thing is supposed to be equal to 0. How can it be if BH alpha H alpha is 0? No. So the only way this equation can be satisfied is if this quantity is not 0. Right? If this is 0, then of course this can never be 0, because this is certainly, this is a dimension. So this is a non-negative number, right? So this cannot be, and in particular for n equal to 0, you see, n equal to 0, we already have d beta. D beta is not 0 because we said beta exists, right? Beta is a root. So d beta is a dimension of g beta. The g beta should have at least dimension 1, right? So certainly the n equal to 0 term gives you just that, and that is not 0. That times some non-negative, a positive integer, right? So this gives you the n equal to 0 term gives you a positive number. Okay. And we are saying this whole thing is 0, but that's impossible unless this was, if this was 0, it would be impossible, right? Because then all the higher n terms just do not contribute, right? Is that clear? So this is the way to prove that BH alpha, H alpha is not 0. But this argument will repeat again and again. This kind of argument, to use kind of invariant subspaces, right? With respect to this subalgebra. Okay. Yeah. So this proves that this is cannot be 0. This cannot be 0. Okay. What else was it in that? Yeah. Now we go to the third point, which is to prove that actually dimension of G alpha is 1. Is there any questions? Are there any questions? Yeah.
We get the last slide.
Huh?
How did we get the last slide?
Okay, so let's write it down. Let's open it up. So let's open up this equation. So I will take out the n equal to 0 term, because this here all the n's are there, right? So n equal to 0 term just gives me b h beta h alpha, right? That is n equal to 0 term. But then you have no, sorry, this is not, the sum is not here. I did a mistake here. B h beta, and here is the sum. Sum is here, and belonging to the integers. No, sorry, no, it's correct. This is that, and belonging to integers. Okay. Now, if this was 0, then there is no way I can make this right. Then we have other terms, which is n times. So let's say 1 times bh alpha h alpha. Then you have 2 times, plus whatever the possibilities, whatever the n's are. No. But since this is not 0, okay, and if this was 0, there is no way I can cancel that, because dimension is always non-negative integer. So you see what's going to happen here. So let's write it down. So you have d beta plus n alpha summed over n. That is the first term. Okay. And the second term is summed over n b h alpha times again d beta plus n alpha. Okay. And this is n belonging to integers. Okay. Now here, if you look at that, this is not 0. This is not 0. Okay. These are all non-negative integers. These are dimensions, right? It could be some positive or 0, right? But it cannot be negative numbers. So each term here, each term in the sum is either positive or 0, right? But surely for n equal to 0, d beta is at least 1, right? Because we said the beta exists as a root. No? So at least for n equal to 0, d beta is greater than or equal to 1. Okay. So already for n equal to 0, you got, so this I can take out, right? This I can take out. So basically, because this does not depend on n. So here you have n belonging to z. No? So there is some number, non-zero number. But this number is for sure positive, because already for n equal to 0, d beta is greater than or equal to 1. Okay. Now it could be that for all the other n's, this dimension is 0, but that doesn't matter, right? It's going to be, so this is certainly not 0. Okay. Now if bh alpha or h alpha happened to be 0, there is no way I can satisfy this equation that this whole sum is equal to 0. Okay. That's the, yeah.
We have proved that if we have space that is that has a matrix that is non-degenerate, any subspace from that space has also a matrix that is non-degenerate. That's our claim? Or?
No, metric. The metric is here. I'm just using the full Lie algebra, right? But this thing is not used. This thing is just used for the what do you call to say that this is zero. I mean to use the cyclicity property. This part is in the full Lie algebra, right? Add H alpha is equal to the commutator up to some number, right? This number. No. This is in general true. In the full Lie algebra itself, right? But now what we are saying is that we can actually consider some invariant subspaces such that these three generators do not take you out of the V. If it acts on one element of the V, it will keep you within the V. No? That is the, and then I can use a cyclicity property. I mean, this thing is needed to be able to use cyclicity property. Right? Otherwise, I cannot say anything about it, whether it is zero or not. Yeah. And notice that this is a similar kind of argument which is, remember for SU2, when we are looking at all the spin J representations of SU2, right? How did we conclude that J had to be integer or half integer, right? And in fact, there was a relation between J and how many steps you can go down. And we found that for every m quantum number, there was a minus m quantum number, right? Which we could all have deduced directly by just saying that a joint of in any representation, R of sigma 3 is the commutator of R of sigma 1 and sigma 2, or R of sigma plus and sigma minus, right? And then we use the cyclicity property to show that that's zero. So therefore, the sum of all the eigenvalues of the sigma 3 quantum number in any irreducible representation must be zero, right? That was exactly the same type of argument. So this kind of chains that we are constructing, this is called a chain. I mean this space, no? We constructed the V which was equal to the sum of G beta plus n alpha n belonging to integers. This is basically what we are saying is this is a representation of these three generators, X alpha, X minus alpha, and H alpha. Yeah, they basically satisfy an SU2 subalgebra, right? You can see this because we already saw that add X alpha, X minus alpha gave you up to some number H alpha. So it would be X alpha, X minus alpha times H alpha. But then add of H alpha. So this was the commutator X alpha, X minus alpha. Okay, this was that, and H alpha with X alpha is what? Is simply alpha H alpha times X alpha, right? Because this is in general true. H with that is H X alpha. Right? But now I look at some particular element of the Cartan subalgebra, so it is that. And H alpha with X minus alpha is the same, with a minus sign. So you see, these three generators form a subalgebra, right? Commutators of any of these, any pair among these three gives you back again an element in this tree. No? Yes. So this forms a three-dimensional subalgebra. Okay, and all this construction of the V that we are constructing, we are writing down, is a representation of these three generators, because these three generators keep a state inside here and takes it back again in the same space, right? So it's a representation. So we are taking this big adjoint representation, which was m-dimensional, m by m matrices, but I'm taking a smaller one, which is what I was calling k-dimensional representation. No, they say this is the dimension of the space is k, which will be some subspace of the full space. So we are constructing a k-dimensional representation from that. And in that representation, the trace of H alpha is 0. Okay. So this is the same like what we did for SU2. That is that. Okay. Now what was that? Yeah. So this proves that this BH alpha H alpha is not 0.
Can you prove the same thing using the degeneracy of the metric on subspace?
Degeneracy of the?
Of the metric on a subspace, for example, V. I think we can do that by just using the mathematical logic.
Yeah, but you see, I mean, how do I know? See, H alpha is just some particular element in the Cartan algebra, right?
Yeah.
Of course, non-degeneracy is what we used to say that there exists some beta such that BH beta H alpha is 0.
Because this is true for non-zero H alpha and H.
No, I mean, non-degeneracy is a well, I mean, it could be. It's a complex. I mean, think of this. I mean, let's say if I take sigma plus. I mean, sigma plus with sigma plus, trace of that is 0, right? Even though in terms of sigma 1, sigma 2, sigma 3, if I take the trace sigma I, sigma j, this is delta ij, right? Or a factor of 2 maybe, some number like that. Huh? Okay. But here you cannot, because we are complexifying the space, right? You're not guaranteed. How do I know? I mean, H alpha could be some complex combination of the Cartan subalgebra elements. Huh?
If we consider the B matrix in the Cartan subspace,
Yeah.
then the degeneracy means that the determinant of that matrix will not be 0. But it doesn't mean that the diagonal elements are not.
Yeah,
So we are actually putting the diagonal elements.
Yeah. That's the point. Yeah. So so this, I mean, as an example, sigma plus, for example, because we are complexifying the whole thing, so it is not. So it's not obvious. But what this is saying is that it is not the case. I mean, it is.
It refers only the diagonal elements.
Sorry.
It refers only the diagonal elements. The diagonal elements.
It reverses the diagonal. If you choose this basis, H alphas. I mean, H alphas, of course, are overdetermined, right? I mean, even if you take SU3, you have alpha 1, alpha 2, alpha 3, right? But the dimension is only 2. I mean, the Cartan subalgebra is 2-dimensional, right? So this is kind of overcounting, but it doesn't
So
matter.
if we say that if we consider any element of the Cartan subalgebra, then we are proving that the Cartan killing form of that element of Cartan subalgebra will itself will not be 0.
That's
But
right.
it doesn't, but the degeneracy of the killing form doesn't imply this.
That's right, exactly. That's the point. It's not immediately obvious, but this is a proof. Right? Okay. Then the last step was to show that the dimension of each of these spaces is 1. So can you raise this part now? I mean, I'm still not finished. I have only 2 more lectures now, right? I don't know how I can even finish what I want to do. Let's see. So the last one is to show that third of that same theorem is dimension of G alpha is equal to 1, and G and alpha is empty except for n equal to 0 or plus minus 1. So there's a statement 1 to 2. So once again, we use the same kind of an idea. And this time what we do, so instead of taking this big space, what we do is we take another space, which is not that, but almost like that. So I take this space, which is a one-dimensional space, a complex number, times x minus alpha. So I've taken some x alpha from the G alpha space, and I've taken some x minus alpha from G minus alpha space. So I just pick that one x minus alpha. It may be higher dimension, doesn't matter. I just pick one, the x minus alpha. So it's only one dimensional. That's the important point. One dimensional plus the h plus again another one-dimensional space H alpha. So this is again one-dimensional. And then consider all n greater than or equal to 1 G of n alpha. Okay. So I don't have any data now. I mean, here we are looking at the space. I mean, we had a data such that some particular beta which was characterized that this is not 0, and then we consider a chain. Okay. Yeah, this was. This was like in the SU2 case, SU3 case. Remember, we had alpha 1, alpha 2. So I take, suppose alpha was alpha 1, and this is beta, let's say. Then the chain would be this, right? This SU2 chain. I mean, this SU2 moves you like that, right? So that chain would have been this chain. So alpha 2 and alpha 3. Alpha 3 was alpha 2 plus alpha 1. No? But now we are just taking the chain, alpha itself, x minus alpha itself, this chain. Now this chain also is invariant. The reason is, so invariant under the action of x alpha, x minus alpha, and h alpha. Right? Because if I apply x alpha on x minus alpha, I'm going to get some number times h alpha. So it moves you. So x alpha takes you one step up, right? And x minus alpha would take you one step down. But the point is that it will not take you further down because x minus alpha with x minus alpha is 0. Right? And h alpha, of course, each of them is an eigenspace. So h alpha takes a state here and back again, the same state, same space, right? So you see, h alpha takes you within each of these spaces, subspaces. X alpha moves you one step to the right. X minus alpha moves you one step to the left. So from here, then x minus alpha x, you get that. Huh? From there, x minus alpha x, you get here, and so on. But the last one, because I have chosen x minus alpha itself, okay, the commutator is at 0. Okay, so add x. These are all add x alpha, and this is add x minus alpha. Add x minus alpha, annihilates that. Huh? So this space is closed under the action of x alpha, x minus alpha, adjoint of x alpha, adjoint x minus alpha, and adjoint h alpha. This space is closed. Now repeat the same thing. Trace of h alpha, so bh alpha, bx alpha, x minus alpha, that's equal to trace of trace of h alpha, add x alpha, x minus alpha. So same argument. So since in this space V, not that space, this space now, this space V, equal trace, then this is 0 from the same argument, cyclicity argument. And now we can directly compute this because I know the eigenvalues for h alpha, these are all eigenspaces. So you see, so for the first guy, this is one dimensional, so this trace will just give you one term, and that's going to be minus alpha h alpha, right? And it's one dimensional, so there is only one. Here, this will give me 0 because h alpha commutes with h alpha, it will be 0. And for the remaining guys, I will get here n greater than or equal to 1 and n alpha h alpha times the dimension of the space of the, so this is the dimension of this is say dn alpha. We don't know whether it's 1 or not, right? But it's whatever, some integer, some non-negative integer. So that's that. But alpha h alpha is nothing else but b h alpha h alpha. Okay, and that we've already proven previously that that's not 0. This is not 0. So this is a non-zero number. And you find here minus 1 plus some n greater than or equal to 1 and this has been taken out and dn alpha. Okay. So now you see these are all non-negative integers. Right? Now how can I satisfy? N is non-negative also. So how can I satisfy this equal to 0? We want to set equal to 0 because we know that this is 0, right?
D of n alpha should not be equal.
Exactly. So the only possibility is for n equal to 1, d of alpha, n equal to 1, d alpha is 1, right? And for n higher than that, n 2, 3, etc., this all better be 0, right? So that's the idea here. So d alpha. So this concludes that. Yeah. So d alpha is 1, and d n alpha is equal to 0 for n greater than 1.
And we cannot say anything about d n equal to 0.
D n.
N is equal to 0, then we does this. Okay.
I mean, our space started with n greater. I mean, n equal to 0 was already this, and n equal to -1. But we are picking only one-dimensional subspace there. And here we take the full space, whichever the vectors are n alpha roots. No, I take them. No, so it need not be one-dimensional at this stage. But what this argument is saying is that the only space which exists here is for n equal to 1. Everything else is empty. N equal to 2, 3, 4, etc. They are all empty. And furthermore, for n equal to 1, this is one-dimensional. Okay. And you can do the same thing other way around. You can construct a space which starts with the, I mean, this only shows for n positive, right? But you can take another space which is v equal to, you terminate the x alpha, okay? And take the lower ones. So plus this h alpha, one-dimensional space. And then take all the g minus n alpha, where n is greater than or equal to 1. Do the same thing. This will be also closed because, I mean, x alpha will move you up, but when you arrive here, a commutator of x alpha with x alpha is 0, so it doesn't take you anywhere else, no? Whereas x minus alpha is going to just move you across back that way. But when you take again the trace, you'll again find that the only possibility is for n equal to 1 here, dimension should be 1. Okay, and for any greater than n minus n equal to 2, 3, 4, etc., all the dimensions are 0. So we are seeing that we are coming, I mean, essentially coming back to like SU3 type of structure, no? This, in SU3, this is exactly what we found. I mean, we don't have alpha 1, there is no 2 alpha 1, no? If you have alpha 2, there is no 2 alpha 2, no? And not only that, there was only one x alpha 1, I mean one dimensional, that space was one dimensional. X alpha, minus alpha 1 is also one dimensional. But what this is saying is that it's not something peculiar that happened with SU3, some accident that happened with SU3, no? This is a general structure for all semi-simple algebras. That's what it is saying. Okay, now what I can do, let me see. I hope, can I take some more time? It's, let's see, we have proven this theorem 12.4, and now there is now, so how to do it? I will need half an hour. Half an hour to complete this chapter, you know. Because there's not much time. I'm doing 2 lectures now, right? Is it 3? I thought one day there was something going on. I don't know, some.
On Wednesday we don't have a lecture.
Wednesday we don't have lectures, right? I don't know why it was the case. I think there was a colloquium or something. No, but it should not. But anyway, my lecture is in the morning, so why should we?
Well, we can have a lecture.
But can I take, I mean, or your concentration now is a limit. I mean, it's natural, I know, I understand that, you know. There's a limit to how long you can continuously concentrate. It's clear. What do you say? I mean, if I can just, let's see, maybe I can just say one more thing and then stop. Yeah, just to say this, I mean, so now we have the yeah, so We are not doing this. Good. Yeah. So the structure, see again. So that's what I said. The SU3 structure is very much there now, right? So what we are saying is, if you look at the algebra now, okay, H with H, HI, I mean in general, some H with H prime, HI with HJ, HI, HJ, etc. belong to the kappa subalgebra. This is 0. That's the definition of kappa. And then we said that HI acting on X alphas. I mean, so these are the root spaces, alpha HI, X alpha, right? That's just a root space, so definition. And the X alpha with X beta, so both are non-zero roots. Now there are several cases. Now if alpha plus, so if beta equal to minus alpha, if beta equal to minus alpha, then this is nothing else but B X alpha, X minus alpha, H alpha. This we already saw. And then so that this means alpha plus beta equal to 0, right? So this is if alpha plus beta equal to 0. Then now suppose alpha plus beta is not equal to 0 and alpha plus beta does not belong to the set of roots. Then of course it cannot be there because there is no such element in your Lie algebra. So right hand side must better be 0. Right? Finally, if alpha plus beta is not 0 and alpha plus beta belongs to the set, then we know it has to be something X alpha plus beta times some number. We don't know what that number is. Right? Question is, can we somehow prove that this number has to be non-zero? Right? This is what we saw in the SU3. We had an alpha 1, alpha 2. The sum of alpha 1 plus alpha 2 is alpha 3. Right? So we know that this is going to be proportional to alpha 3, but it could have been 0 times alpha, X alpha 3. Right? But we saw that it was not 0. It was some number, no, non-zero number. Right? So question is it a general statement, no? Or is it just an accidental feature of SU3? And one can prove again from semi-simple thing that this is non-zero. Okay. I don't know, maybe you can. But how can I mean, one day, I mean, surely this 3 hours is not enough. 2 lectures means 3 hours is not enough.
Maybe we could take a lecture on Wednesday.
I have to check with, I don't know what is the reason for me.
There's nothing on the schedule.
Nothing on the schedule.
So, possible.
Okay, I will check with Patricia, but there must be some reason. Is it a holiday or something?
No, because we have lectures on
Okay, so I will check with Patricia. If it is possible, I will, again, yeah. Because 2 lectures is not enough. I mean,
That's enough for what?
Am I finishing the whole lecture notes in me?
no, I cannot finish all of it anyway.
Okay.
That's impossible. But at least to arrive at a point where, I mean, yeah, something more.
Baking diagrams?
Huh?
Baking diagrams?
Baking diagrams I cannot do.
Hey.
That's the best, right? I mean, I agree with you. Yeah, I agree with you. But this is, it's impossible even within 3. But what I wanted to do was to, we have to still discuss the classical algebras. You know, we discussed already a bit. SON, SUN, SON, and SPN, symplectic groups. And to show how this fits in this language, the roots, root systems and so on. But maybe that I can leave it as a kind of exercise to just go through, because it's very straightforward. I mean, these are general thing. There it is just explicitly working out what are the roots, what are the, so it's not so complicated. It's just a matter of going through that chapter. There's nothing conceptually the matrices, just work out the commutation relation, find the roots, eigenvalues. But then I wanted to give you an example of rank 2. You have example, you already seen SU3. Rank is the dimension of the Cartan algebra. You have the SO4 also has dimension rank 2. SO5 also will have rank 2. Now these are all classical algebras. SP2 will also have rank 2. Okay, but these are what we know, right? But from this kind of arguments, we can construct a completely new algebra which was not obtained from any of these matrix groups. This is a G2. So that would be nice to see how, from the general formalism, you can get more than what you knew from your matrix groups. Okay, yeah. Okay, let's see. I will try to see if but you are opposed to the 3 lectures, is it? You didn't want 3 lectures.
No, it's fine.